Hi there, this is Bobak Bike continuing with these meteorology lectures. Sorry that I might sound a little bit off. I might have already said this in the last one, I can't remember, but I kind of have lost my voice a little bit, so it's of course, but I'm still going to make this video. Um, Energy and heat is what we're going to talk about here. So, might seem kind of boring, but it's very important because this is the very stuff that affects the weather. So, for me, what I'm the most interested in is, um, well, things like in this picture. Might have mentioned it before. I took this picture in Colonial Beach, Virginia in 2020. I've always been really fascinated by storms in particular, and you may be as well. And this is the stuff that we have to know to get to that, like to understand why things happen. Well, first of all, energy. Um, we hopefully know that it can only be transformed or converted. It cannot be created or destroyed now. Like that kind of depends on if you're talking about an open or closed system, but realistically, that we of course are thinking of an open system when we're talking about weather, so can't be created or destroyed. Um, there's more that you can go into that, like with the laws of thermodynamics, and I just am not going to talk about that right now. Um, it's measured in joules, has a unit of J or watts. Um, Energy from the sun is the most important to us, for our purposes. What is heat? Heat is produced by random and chaotic motions of molecules and atoms. Um, we typically associate heat with warmth, but it is more than just that. There's something called specific heat. Specific heat is not a type of heat, it is an amount of heat. And it is an amount of heat that is needed to increase temperature of 1 gram of something by 1 degree Celsius. Of course, I've already said Celsius, very standard unit that we use. We can see that the thing with the high specific heat is water. Um, Next is ice, then air, then sand. And that is really crucial that you know that order. Um, but yeah, you can look at this table to see the relationship between them. And as you can see, water has the highest specific heat. Um, Energy is able to be transferred by three different primary ways. First is conduction. Conduction is the transfer of energy by passing from molecule to molecule. This is not so much the case for weather. The second and third are more what we're going to talk about, but this is still important because like if you touch like something that's hot or you touch something that's cold, the reason why you get those sensations is actually because energy is being conducted. Um, and energy always will go from high to low. So when you're touching something that's hot, you are the thing that's colder. So as a result, energy is conducted, a whole bunch of it all at once at in you. And that's the reason why you feel that you got burnt. But it's the opposite for ice. Instead, energy is going to the ice and melting it. The second transfer mechanism is convection. Um, this is when energy is transferred through a fluid through molecular movement. Um, we're going to talk way more about this, but boiling water is an example, but also just as convection is a very evident and present thing in the atmosphere. The last is radiation. Radiation doesn't need any medium to travel. It just travels in waves, and we're going to talk about the second and third in detail. First, convection. Convection circulates heat. Um, Free convection, there is forced and free convection. Forced is not really important for us. As you can see, forced, that means it's not something that's and specifically naturally caused process, but free convection is, so that's why this is what we care about more. Um, Earth or air near the surface of the Earth heats up and rises. We know that hot air rises and cool air sinks. Something that's cold is heavier, that's why it sinks, and the reverse is true. Um, so that's what free convection is. We're saying this is always going to happen. So this statement is something that you need to ingrain in your brain to know that it's true, that that's what will happen. Heat will rise, cooler air will sink. Um, More on radiation. Um, when we're talking about radiation, we can use the unit micrometers. The electromagnetic spectrum, you may have seen this before. It tells us about electromagnetic radiation that is emitted by the sun and transferred to the earth. Over here, these are shorter wavelengths. Since they're closer together, these are longer wavelengths. You'll want to know the order of these, but these are not really that important for us in meteorology as um, the longer wavelengths. Um, but so gamma rays, X-rays, they are really not relevant to us. UV, ultraviolet is not really specific to weather, but just in general, um, we know that it's damaging to humans, and this is why we get sunburn. Um, ozone layer, our ozone layer is what helps keep that out. And when you put on sunscreen, it's almost like a mini ozone layer on you, which is the reason why that works. Visible, that's just what we can see, the rainbow, you know. Infrared is actually the most important, um, because it is what is the heat that we receive from the sun. Um, Microwave, FM, AM, not really as important, but you would just need to know the order. Black bodies. What is a black body? A black body is not really something that exists, but we use it to explain how that something would be considered a black body if what goes in comes out exactly. Um, and that means it's a perfect emitter of energy. But we like, what's the point in even saying this if it doesn't exist? Well, the sun and earth are close to black bodies, so we're like almost. So that's what we're meaning if we say the earth is almost a black body. We're saying that everything that comes in mostly goes out. All right, let's talk about some radiation laws. Um, Energy in this Stefan Boltzmann law is proportional to temperature. So what do we see here? We have I, which is energy, is equal to that symbol right there. This Greek letter is what we call the Stefan Boltzmann constant. I already said in the last lecture, if you don't know what a constant is, it's something that is always the same. It's always going to be 5.67 to or times 10 to the negative eighth. That's what it will always be. And it's going to always be multiplied by temperature to the fourth power. Temperature, you see this is really big, needs to be in Kelvin or your calculation will be wrong. So here's a little table of how you can convert between the three units. Um, Celsius to Kelvin and reverse is the easiest because 273 is what you add or subtract. If you want to do Fahrenheit to Kelvin, which isn't even on here, you would first convert to Celsius, then Kelvin, which is harder because you would have to do Fahrenheit minus 32 times 5 over 9. I mean, it's not hard, but it's just more complicated. Decimals, you know. So just remember, temperature needs to be in Kelvin. But what can we say about this law? What would happen if temperature increases? The I would, because I mean, this isn't a denominator of a fraction. If you increase this, it's going to make this bigger. So hotter objects emit more energy. Uh, this next one, Vane's law, is used to determine peak wavelength. Um, so this symbol that looks kind of like upside down Y is wavelength, and max, so peak wavelength. And it's equal to 2900 divided by T. Once again, must be in Kelvin. But this time, unlike the other equation, temperature will have a inverse effect on this. Since it's in the denominator, the bigger that it is, the smaller this will end up. So hotter things have shorter wavelengths. Now let's talk about shortwave and long wave radiation. We know what that means based on the graphic I showed before of the electromagnetic spectrum. Shortwave radiation is the most intense on the visible spectrum. It is what comes in as solar radiation. So things that come from the sun are short wave radiation mostly. Long wave radiation is emitted from the Earth's surface. So what happens is the sun emits energy to us, and we're going to talk more specifically about like the amounts of what is absorbed and reflected back, but the Earth actually reflects back energy, and it comes in as short, it leaves as long. So it gets reflected back as long wave radiation. And this is really important. At the beginning of this video, remember I said like why you might wonder why this would be relevant. Well, this slide is pretty much the main one that tells you why. Because energy can get trapped at the tropopoles. Um, and this is what leads to weather. Um, specifically even severe weather. So that's why it's relevant. Let's talk about the types of heat. So remember, we talked about specific heat, and I told you that wasn't a type of heat, it was an amount. These two are types of heat. Sensible heat, as the name suggests, is heat that we can sense. It's what we consider heat, you know? It's added to a substance and it can increase temperature that we can physically sense. Latent heat, on the other hand, is energy required to change phases. So it's heat that may be released um, or taken from an environment due to a phase change. So hopefully remember the three phases. We have solid, liquid, gas, and for our purposes, that's going to mean ice, water, water vapor. This is a very important thing to look at here. So let's go through all the combinations. So let's start over here. Ice going to liquid, that's going to be melting. Energy is taken from the environment, and there's actually cooling of the environment. That might seem opposite of what you would expect, but that's actually what happens in terms of latent heat. And when energy is taken from the environment, there's cooling. That might make sense. But why is energy taken from for melting? Well, there has to be energy taken in order to melt. Then we go to evaporation, same thing. There's going to be cooling, opposite way. If we go from water vapor to liquid, that is condensation. Well, when there's condensation, energy is actually released, and that's warming. And then liquid to ice, freezing, warming of the environment. So that's something that might really seem odd, but that is how it works. Then we have two more that are pretty rare. We can go from ice to vapor, that's called sublimation, and we can go from vapor to ice, which is deposition. But that is very uncommon to go skip the middle one. Let's look over here to see how much units of energy, which we'll assume is joules, um, is needed. So we can see condensation 540, deposition 680, melting 80, evaporation 540. So it's about the same for these two. Same for these. And then you can see melting and freezing. It takes a lot less to go from ice to liquid as it does from liquid to vapor or vice versa. When we're talking about the energy budget, we are explaining the balance between incoming solar radiation and outgoing terrestrial radiation. So we're going to say we have incoming solar radiation. Some's going to be reflected back to the atmosphere. Some will be reflected by clouds. Some are reflected from the Earth's surface. And then there's a lot that's absorbed. And there's also conduction. Remember, I talked about that. Um, There's radiation as well, also talked about that. So it's kind of just an even process. Back to what I said about black bodies. It's almost perfect that it's even that what comes in goes out, but it's not perfect, but it's close to perfect. Remember the gases that we talked about in the last lecture? Um, most gases are selective at absorbing incoming radiation. For example, UV radiation mostly only absorbs, or sorry, that's backwards. Ozone, the gas ozone, mostly only absorbs UV radiation. Visible light is not really absorbed at all, and that's what we end up seeing. What can happen to energy? So we know the types of energy, we can know how it can be transferred, but what can happen to it once it's in here? It can be, we have transmission. This doesn't really affect the energy. It's kind of just moving to a different form. Reflection is going to be the redirection of energy. Albedo is knowing the albedo can tell us the reflectivity. So it's the percent reflected. We have a high albedo. Whatever surface that is going to be light and it's going to reflect. However, low albedo, it's going to absorb dark. So that explains why when you wear darker clothes in the summer, that's kind of dumb to do if you don't want to get super hot, because everything's going to be absorbed because your shirt has a low albedo. Um, Scattering. Energy can also be scattered, in which it is diffused in all directions. There are three types of scattering, and let's talk about them. Rayleigh scattering, Rayleigh, however you want to say it. This is scattering particles that are smaller than energy wavelengths. Why is this important? Well, this is what causes the blue sky. So if you ever wondered what causes blue sky, it is Rayleigh scattering. This is energy that's coming in, it's being scattered. And what way is it? Rayleigh scattering. Um, Blue has a short wavelength, which explains why. And as another side note, the less moisture, the more blue. So this sky right here in this picture, I took this picture in 2021. Well, the sky, it is blue, but it's not as blue as skies can be. And the reason why is that there is definitely a good bit of moisture considering the environment right here. I mean, look, we have a river here. We also have clouds here. The second type is me scattering. Me. Me, my, me, whatever, however you want to pronounce it. This is aerosol-based scattering. If you don't remember what aerosols are, please refer back to the other video. But examples include um, dust, um, debris from forest fires, things like that, pollution. So whenever you have a forest fire, there's actually going to be really good sunset because me scattering results in color coloring of sky, which is why we can get haze and sunrise, sunset. This is also a picture I took of probably the most colorful um sunset I ever saw. It was a very odd day. But I'd have to admit that that picture I think is more colorful than it actually looked, slightly, because that doesn't really look realistic to me, but whatever. Um, Non-selective scattering. This is scattering by clouds, and this will cause a white or gray appearance in the sky. The more ice and water that you have in clouds, the less reflecting that they can do, and we will get darker clouds. What happens to energy as a whole? Assuming that the incoming energy is 100 units, this is just hypothetical. Let's just say what comes in is 100. Well, what's going to be absorbed is 25. What's going to be reflected is 25. Um, sorry, absorbed by the atmosphere, 25. Reflected, 25. Absorbed by the surface, 50. We consider that we have an energy deficit if what is absorbed um, is less than what's emitted, and the opposite is surplus. Wait a second. That is not, I don't know what's wrong with that. I apologize. It's supposed to be it what what's absorbed is greater than emit. I didn't mean to do that. Sorry. Um, Greenhouse effect. Hopefully you know some about this, but the greenhouse effect is when gases are trapped by uh, terrestrial radiation. So it's important. A common misconception is that the greenhouse effect is from the sun's radiation coming in. No, we're actually saying that the radiation coming up to terrestrial means it's coming from the Earth. What's reflected back is being trapped, not what's coming from the sun. And this is very important because if it didn't exist, the temperature of Earth would be way too low. Um, but these are some greenhouse gases. We know CO2 is on the rise. Well, this is why there's global warming. That is it for this video. Thank you for watching. Hi there, this is Jacob Nash. This will be the third lecture for meteorology, and we're going to talk about the significance of Earth's tilt, sun angles, zenith angles, solar declination. Let's get started. And don't know what that means, that's fine because that's the point of why you're watching this. Well, what causes seasons? A lot of people, more people than not, actually think that it's because distance that the Earth is from the sun on its orbit. That is incorrect because you might not know, but the Earth is actually closer to the sun in winter. So that's not the reason. The reason is the Earth's tilt. It's tilted 23.5 degrees. Geometry is very cool because that 23.5 degrees happens to be where we have certain latitudes that can achieve 90 degrees of radiation. So direct. And that's just, I'm not going to get into the specifics, but that should make sense in terms of geometry. We have a 23.5 degree tilt, so it only makes sense that those degrees of latitude are the ones that could receive direct sunlight. So these latitudes that you're going to want to know, 23.5 degrees north is the Tropic of Cancer. I, if you know the show Seinfeld, you might know there's one episode where Jerry, the one of the main characters, supposedly has an overdue book, Tropic of Cancer from 1971. Well, what's the point? Like if you even know that, which you might not, anything about the show. Well, you know that it's set in New York, and so I always think of George saying Tropic of Cancer, and that's north. So that's how you can remember which is which. Tropic of Cancer is the north one, the one that's closer to us, closer to New York, closer to George. Equator is at 0 degrees. Tropic of Capricorn is 23.5 degrees south. And in between this 47-degree area is what we call the tropics. So you've probably heard that so many times. The tropics, the tropics. This is what the tropics actually are. And it's not by chance that they are where they are because that 47-degree area is the only area on Earth that can actually receive 90 degrees of a 90-degree sun angle. It's just not geometrically possible outside of that. When do all three places get a 90-degree radiation? The Tropic of Cancer gets it in the summer, specifically at the summer solstice, right on that day, which is June 21st, roughly. Um, Now that makes sense, right? Because Northern Hemisphere, we in the summer solstice in June 21st, it is summer for us, right? In the north. So it makes sense that that's where the north part is where it gets the direct sunlight in the summer. It's the opposite in the winter. Tropic of Capricorn instead is the one that gets on December 21st. The south is where there can we would consider summer. Um, then the equator is where they get it in the fall and the spring, on the equinoxes. So September 22nd, March 20th. But like I said, nothing outside of the tropics are able to receive 90 degrees of radiation. So sun angle, solar elevation, elevation. Sorry, I'm kind of a little bit tired and not feeling well, so can't speak elevation. Um, 90 degrees is only possible. I just said that, sorry. Um, now, well, what is the reason that the lower the sun angle is not as warm? Like, because think about it. Okay, here's the sun angle. It's going to be based on distance above the ground. If the sun angle is smaller, the sun's going to be like right here. Well, it has to pass through a longer distance through the atmosphere, and some of the radiation is, as we've known, absorbed by the atmosphere or reflected back in some way. So less gets to us. That's the reason. Amount of daylight, as you may know, is also affected by sun angle, daylight hours. Well, the thing about equinox is equa is the prefix of that word, which means equal. You might not know, but on the first day of spring and the first day of fall, everywhere there is 12 hours of daylight. And but the sun angle is not the same everywhere. Geometrically, that's not possible. I've already said that. But it's in the winter and summer that it varies greatly. There's actually at the poles, um, there can be almost 24-hour days or 24-hour nights. So I'll say something as an example. Um, I know I have a friend that is in Sweden, not even southern Sweden, Stockholm, it's northern Sweden. And let me just look right now. So sunrise is 6:37, sunset is 6:19. That's actually pretty similar to here. Why? Because the day I'm making this video is on September 26th, and that is very close to the equinox. So that is why it's similar to here. But fast forward or backtrack, whichever you prefer, if you go back to June or ahead to December, it's going to be way different there. And they're going to have either really long days or really short days. Solar declination. This is a latitude, and it is the specific latitude where the sun is 90 degrees. I already said a solar declination is not possible outside of 23.5 degrees north or south. Just not possible. Geometrically, it's just not possible. The declination is, no surprise, 23.5 degrees times sine of n, where n is the number of days to the nearest equinox. So n, I would put, I think the first day of fall was on the 22nd, so I would put 4. And if I put that in, 23.5 times sine of 4, that would give me the solar declination, which is a latitude. Um, Now think about it. If the number of days to nearest equinox is 0, meaning that it is fall or spring, um, I would put in 0. Sine of 0 is 0. And as a result, um, that means that the solar declination is 0 degrees. So at 0 degrees, there is 90-degree sun angle. Remember, just because everywhere has 20, or sorry, 12 hours of daylight on the equinoxes doesn't mean it's the same sun angle everywhere. No. Our It means that uh that the sun angle is going to be 90 at the equator, which makes sense if it's right in the middle. Might that make sense of why we all have equal daylight? Zenith angle. Well, first of all, what is a zenith? A zenith is, in this case, the point that's directly overhead. So 90 degrees. So if you look up and you see something on the ceiling that's right above you, that is your zenith. But the zenith angle is the angle between the zenith and the sun. So I'm looking up at my ceiling right now. I Let's say I see a black dot on the ceiling. Maybe I like hit a broom on there or something like one day. I don't know. So I see a spot on the ceiling. The angle from that to the sun is the zenith angle. Um, and that's gotta equal 90 degrees when they're added. Um, so you can say the zenith angle plus the sun angle is 90, or define the zenith angle, it's 90 minus the sun angle. Another way to look at zenith angle, we can also calculate it by our latitude of interest plus or minus solar declination. Remember, solar declination was 23.5 degrees times sine of n, where n is the number of days to the nearest equinox. Latitude of interest, so that just means whatever we want to know the zenith angle. So I want to know the zenith angle of uh, Tallahassee. Okay. So I figure out the latitude of that, and then I figure out the solar declination um at this point at now. Like, so I would plug in 4 for n of that zenith, or sorry, of the solar declination equation, and that would tell me the zenith angle. Now, if the solar declination and latitude of interest are in different hemispheres, then we're going to add. Rarely for our purposes will that be the case. So we're going to subtract if they're in the same. So right now, they actually are indifferent. So, and that's actually not really true. That's not true that that's rarely the case. I was thinking of something else, sorry. Um, so it could be either one. So right now, if I was to do this right now, like my example, Tallahassee, I would actually add them because the solar declination is going to be in a different hemisphere right now. How come? Well, I know a few days ago it was 0. It was at the equator, but I know right now it's going to be more towards the southern hemisphere because we're getting closer to winter. And in the winter, that's where the sun is at 90 degrees in the southern hemisphere. All right, this table is important. It's kind of wrapping up what we've talked about. So we see two different locations right here. Um, so the first is Winnipeg. If you don't know where Winnipeg is, it is in Canada. So that gives you an idea of where it is. Austin, I hope you know that. That's in Texas. And also, by the way, I'm assuming you're American watching this, so you might not know Austin if you're not American. Um, so we can see right here, there's a difference in latitude. Higher latitude for Winnipeg. Um, and this is December, so this is winter. The solar angle is smaller for Winnipeg. That makes sense, right? And the day is shorter too. And the total radiation is lower. That makes sense, right? Well, what happens over here? In June, it's the opposite. Well, everything's the opposite except for one thing. Still, the solar angle is smaller. But what's the deal here? The length of the day is longer now. Well, if we think about everything that I've just talked about, um, it would make sense that the length of the day is longer at this higher latitude at this point. Um, we also have only a slightly um, higher total radiation for the day, but it is higher this time. And these differences we can consider gradients. There's less of a gradient in the summer, um, which is the reason why weather is more boring in the summer, as some may say. Um, so the reason between these is the season. It has nothing to do with anything else. All right, that will be it for this video. Thank you for watching.